So this is your group 17 hydrogen halide being formed from the gaseous hydrogen and iodine, gaseous iodine. This is an equilibrium. So they really like the equilibrium in this paper, okay? They want Kc. So Kc is to do with square bracket concentration. You square it because there's 2 in front of the stoichiometric balance equation. And then you divide by the concentration of the reactants, okay? And you will know there are no units here because the units will be cancelled out. They haven't asked for the unit obviously, but in a theory paper they really like to ask for the unit. So there's mole per dm cube square at the bottom. They cancel out, so you give you no unit. I don't think you get any marks for doing this, but I'm just showing you that there are no units, as they like to ask you in an MCQ or even in a structured theory paper, okay? So if the starting concentration of both the iodine and the hydrogen was A mole per dm cube, and you get 2y mole per dm cube of hydrogen iodide. So this is a kind of a very common equilibrium Kc kind of question, yeah? So the best thing you could do is really set up an equilibrium table. So I know the equations are given above, but I want to set up an equilibrium table so that I can write out, like things like initial concentration, where I have A and A because both the iodine and hydrogen was A mole per dm cube. I have nothing of the Hi, and then at equilibrium I would have 2y mole per dm cube of Hi. From the stoichiometry, I hope you can see that H2 reacted compared to Hi form. So if you are very weak at this kind of calculation, go through some of the topical playlists on equilibrium constant, on how to interpret what has reacted and what has formed, and how to do more examples of this kind of question, because we just never know when they will come up again, yeah? Alright? So how much of H2 has reacted, that is what you want to find. This is what you started with. I know it doesn't go to 0 because at equilibrium means I still have some of it, of the reactant. I have some of the product. Okay, that's what equilibrium means. Okay, so how much of that has reacted in terms of how much of it has formed. You started from nothing, you end up with 2y. So you have formed 2y mole of Hi. Bottom is for Hi. This is from balance equation. This is actual. Alright, so the mole of H2 reacted is equal to half times 2y, which is y. And you can also see that the mole of I2 reacted is also equal to the mole of H2 reacted, because 1 mole of H2 reacts with 1 mole of I2. So if you react this much H2, then this much of Y2 also reacts. So that is also equal to the mole of I2. So I don't need to do the same thing twice. So that will be A minus Y, because Y mole will have reacted. Now these are the concentration, these are mole, but these are all in the same volume. So when you multiply V total, multiply V total, then they're going to be the same. Okay, because they're all in the same volume. I'm not taking anything out, alright? So our job is not complete. They want the Kc. So realistically speaking, I could have put a bit more space for myself. So if I use a different color, so based on the expression above, alright, so Kc is the Hi concentration, so it's 2y squared over A minus y squared. And again, I'm not making my life easy for myself. You don't leave your answer like that. You always have to simplify, okay? I mean, I'm sure you know this from your maths classes, that you need to simplify your expression all the time, okay? So this is the simplified expression that I could get for the Kc. The expression for equilibrium constant from A part 2, basically this, can also be rewritten. So you want to make y the subject. Make y the subject. So basically they're giving you the answer, right? Make y the subject. Well, you don't have to, but I'm just saying that this is the answer. You can get Kc from this as well, alright? So if I start from here, this is not what the question is asked. I'll just do it anyway. So Kc times A minus y squared is equal to 4y squared. Am I doing this correctly? No, I'm not doing this correctly at all. No. It's not as easy as that. Okay, probably I don't want to do that. What I'll do is, because here you see you have y on top and y at the bottom, it's not easy to make y the subject. What I'll do, see what I can do, yeah? 2y plus y kc is equal to a kc. So a minus y kc is equal to 2y. Then kc is equal to 2y over a minus y. Then kc is equal to 2y squared over a minus y squared. Oh, guess what? Kc is equal to that, right? So we can be sure that this is correct because I can go from here to here. Rather than going from here to here, that looks horrible, but I could easily go from here to here by just doing a bit of mathematics. That is not what the question has asked. I'm just saying that, you can check your answer given the answer is already here in a different form. So in an experiment, you remove A from a 1 dm cube flask. So your volume is 1 dm cube. The amount meaning the mole, okay, of hydrogen iodine gas were mixed together. Then you get the initial concentration as whatever they have told you just now, A mole per dm cube. You're allowed to come to equilibrium. This is at a particular temperature, 760 Kelvin. So room temperature is 298 Kelvin, that is 25 degrees Celsius. So that's 25 plus 273. Alright, so this one in degrees Celsius is 762 minus 273. Equilibrium concentration of iodine A minus Y was then measured. Equilibrium concentration of iodine A minus Y. Look at it. You see, they are very, very generous actually. Yeah, they're very generous at telling you that this is the equilibrium concentration of iodine. Meaning to say, without doing this, you could have gotten the answer as well. So this is a very generous 1 mark. Okay, so you do it for various initial concentrations, and then you record the values in this table below. What do we want? We want y mole per dm cube to 3 decimal place. If you know A minus y, how can you get y? Alright, so if this is column capital A, column capital C, then F capital B, then column capital C is equal to A minus B, because you can try 0.200 minus 0.022, you're going to get 0.178. And you can also see A minus y is equal to A minus A plus y is equal to y. So to get y, you do this minus this, alright? So I'll do the rest of them. Make sure you know it's 3 decimal place. Maybe it's wise to just remind myself there. So this is one of those things your calculator give you 4.45. If you are not careful, if you don't think back on what you remind yourself, 3 decimal place, alright? Based on the question. 0.548. So if you're looking at this on the screen, I really suggest you to actually get to compute this thing to see how careless you can be or how good you can be, and then you should really practice your putting in the graph as well, because that takes a bit of practice. Yeah, it's not like one day you just turn up and then you get very good at it. Okay, so very few people are actually gifted like that. I'm not gifted, so I have to do it the hard way through practice, which you know yourself if you're gifted or not. So give it a try and see how long it takes you. Alright, if it takes you long, practice a bit better so that it will take you shorter time with practice. So that was just for 2 marks for computing all of these to 3 decimal place. Next bit is a plot of graph of how the y mole per dm cube vary with A mole per dm cube. So this is our y-axis, this is our x-axis. Instead of me going back and forth to this table, what I'll do is I'll have the table of results on another piece of paper, and I'll start plotting this graph based on the values. That's what I meant by you should have calculated the value somewhere. Then you can start practicing drawing this graph with me and see how long you take. Alright, very stingy only 1 mark for plotting in the graph. That is very, very stingy. Anyway, when you see the graph, you see there's 1, so there's 0.5. This is also starting from 0, 0. There's 1, so there's 0.5. So since it's 1 mark, let me just get started without wasting any time. All right. So it's plotting y against a. So 0.2 is 0.178. 0.2, so there's 0.5. So this is 0.1, 0.2, 0.3, 0.4. So 2 of these give you 0.1. 0.2 is 0.178. 0.2 is 0.178. Roughly is there. We'll give or take. 0.2 and 0.178. 0.5 and 0.45. 0.5 and 0.4. 0.45. 0.8, 0.548. 0.8, 0.548 is 0.55. That's the closest. 1 and 0.8. 1 and 0.8. 1.5 and 1.135. 1.5 and 1.135. Somewhere there. 2.1 and 1.53. 2.1 and 1.53. 2.8 and 2.148. 2.8, 2.148. 3.4 and 2.7. 3.4, 3.4 and 2.7. 2.5, 2.6, 2.7. 3.8 and 2.93. 3.8, 3.8 and 2.93. So that's close to 2.95. 4.2 and 3.33. 4.2 and 3.33. 3.3, so it's 3.3 is roughly there. And lastly, 4.9 and 3.75. 4.9 and 3.75. 4.9 and 3.75. So that is 3.5. Between 3.5 and 4.0, this middle bit is 3.75. And then 4.9 is just 2 small square before that, because that is 4.5. So 2 small square before that is 4.9. Alright. So we can see there is a straight line. Okay, so there's quite a good straight line there. I'm gonna minimize this a little bit. When there is none of A, there will be none of Y. So we know this will cut through 0, 0. But what you do not do is do not put a cross there, because this is not a point given on the table. But you know you cut through 0, 0 because you can think about what happened. You can think about, so this is what you would do on your ruler. Best fit straight line. Best fit straight line, you want to fit the most number of points. Okay, that's probably my best fit straight line. So some of the points are going to deviate slightly, but when there's no A, and your A was your initial concentration. So if you don't put anything in, how can you get anything out at all? Alright? So that's why I cut through 0, 0. But we don't put a cross there because it's not a point on the table. Okay? So draw a line of best fit, which I just did. Determine the slope of your gradient. So if we go back to our graph, okay, it's not necessarily a point from the table, but it's about a point where the line passes through. Our line passes through 0, 0, so that it can be my 1 coordinate, 0, 0. And the second point, I'll probably go for something easy. Where is an easy one? That seems to be easy. So that is at 2.0. So this thing there, 2.0, and so that was 2.0. So there's 1.5. There's 1.55. So 2.0 and 1.55. Okay. 2.0 and 1.55 is my other coordinate. So it's basically there. Alright. But you have your own line, so you should use your own data. Yeah. So don't be surprised that your value will be different slightly from mine, unless your graph was badly drawn, I guess. Okay. So they just want the gradient. So the slope refers to the gradient. Remember, it was an upward slope. Upward slope means it will be a positive gradient, which I'm sure you know from your gradient classes in lower secondary mathematics. So you use bracket in your calculation because brackets are one of those things which are very, very important. I get that exactly. That is 3 significant. So you might get more decimal place, but it's just down to what value you use. Doesn't matter really. Calculate the gradient, make sure it's 3 significant, and then that's it. So you gotta use your value of your slope, which is a gradient, and the equation in B to calculate Kp, and you must show working. What is your equation in B? The equation in B is y is equal to AKC over 2 plus KC. I'm just writing that out because I don't want to be flipping back and forth. Actually, I should cut that. So on your actual exam, you can flick back and forth between your paper. So you don't do what I do, obviously. So what was the graph you show? Your graph that you draw was y against A. Alright, y against A. So y against A. I hope you can see that is your y-axis. This is your x-axis. And then this means this bit there, it's basically your gradient. There is no y-intercept because there is no constant. Big C, y is equal to mx plus c. Alright, so this is your linear relationship there because our line cut through the origin. So there's no constant there. It doesn't have a y-intercept bigger than 0. So that doesn't exist. So there's just the y-axis. There's just the x-axis on your graph. You plot y against A just now. So your gradient is just all that thing there because there's a constant. There's a constant. There's a constant. At a constant temperature, your Kc doesn't change. Alright. So therefore, your gradient is equal to Kc over 2 plus Kc. Do I want that? Yeah, I guess I can move that a little bit there. Then that can be there. Give me a bit more space to work with. So that's 0.775. That is your gradient from the previous question. So now really your job is make Kc the subject. So Kc is equal to 0.775. Use bracket, alright? I cannot stress that importantly. This whole thing multiplied by 0.775, and this is where a lot of students will have made a mistake. They thought it's just 2 times 0.775. No. This is a plus. This bring up the whole thing. It means this times this, alright? So you know expansion of terms from your, again, I keep on saying, your lower secondary mathematics. But you might have done this in upper secondary mathematics, I'm not sure. But you would definitely have done it in your mathematics before you come to A level. Alright, so Kc minus 0.775 Kc is equal to 1.55. I hope you can factorize this, or at least you can see there is 1 of it. So 1 minus 0.775 is equal to 1.55. Your Kc equal to 1.55 over 0.225. Okay, my working is getting a bit long now. In reality, if you are very good at maths, you can cut down a couple of these steps. But I'm not very good at maths, so so I'm showing everything. Okay, so that is square because it's 1.55 over 0.225. The whole thing square because now I move the square root to the other side. Alright, or you can think about square both sides. When you square this, you will have no square root. Then when you square this, you get that. And you should give your answer to 3 sig fig because we used previous data. That was to 3 sig fig. 1.55 square, 1.55 divided by 0.225. Then you square that. Oops. Then I get 47. Maybe I shouldn't use that much space there. Maybe I can use the space here. Yeah, okay. Alright, So as long as it's labeled, yeah, as long as it's labeled, it should have been alright if you label your step properly. Because I don't feel comfortable writing the answer for one part in the lines of another answer, right? That's 47.457. KC is roughly 47.5 to 3 significant figure, okay? You can cut down some of the steps. I was just showing all the steps because, like I said, I wasn't very good at maths, so I don't want to make any mistakes, all right? Explain why, for safety reason, that you want to remove the A from the 1 dm³ flask. So we know that we had to remove that A, right? So if we have A, what does A contain? So A is a mixture of gases. Mostly is nitrogen and oxygen, which are diatomic, okay? So the oxygen can react with hydrogen from this reaction as a reactant. And I'm not sure if you know that hydrogen reacts with oxygen is exothermic reaction, so can be explosive. Just think about your reaction of sodium with water. You release hydrogen and the hydrogen reacts with oxygen in the air and it catches on fire, alright? So it can be explosive, especially at a high temperature. Because if you remember, you did the reaction not at room temperature. I talked earlier about when you read the question, you did it at 760 Kelvin. That is way higher, 760 Kelvin. So it's just for safety reasons, and you gotta outline why and how is it not safe. All right. Phew. So one of the experiments in B was repeated. You use a 500 cm³ flask. So this is a smaller volume than a 1 dm³ flask. Would that affect Kc? Well, I can tell you it wouldn't, because only temperature can. So since you're just changing volume, you're not changing temperature, that would not affect it. But rate of reaction, yes, because changing volume means that you will change the pressure of the gases exerting on the wall. So this is a classic rate versus equilibrium. Instead of being asked in a theory paper, as you have seen the topical playlist under chemical equilibrium, you will see there's a lot of questions that have been asked in the theory paper 4 or paper 2 on rate versus equilibrium type of scenario. But here is being asked in a paper 5 setting, and it's perfectly within their syllabus or their specification to ask you that, alright? So firstly, I can talk about Kc first. So value of Kc remain constant. They don't ask for explanation. They just ask you to state here, remain constant, or you can use the word unchanged. Alright? Because, Kc is only affected by temperature. Alright? So your equilibrium position can change when pressure changes due to the change in volume, but only temperature can change the value. Alright? However, the rate, you go to a lower volume, so maybe I start explain first. With a smaller flask, with a smaller volume, 500 cm³ of the flask, the gaseous reactant collide more frequently. Can you imagine when you have a big flask and a small flask? In a small flask, you have the same amount of stuff, right? You still have the same amount of, gases, but in a smaller volume, so they will collide more frequently, and therefore the rate of reaction is faster. And again, they don't ask you to explain. I don't know why I have spent some time explaining it. Ideally, it would have been enough if you just say rate of reactions get faster in that smaller flask, and value of Kc remain constant in that smaller flask because you are not changing temperature. Alright. Anyway, if you are in theory paper, you'll be expected to talk about collision frequency based on the changes in volume. You'll be expected to talk about only temperature can affect the value of Kc. They always ask this in a MCQ kind of question as well, yeah? So this is the last two questions on this paper 5 tutorial. In this question, they tell you that the reaction of hydrogen and iodine to form Hi is exothermic. Okay, so what effect would higher temperature do on the value of Kc? So we did say that only temperature can affect value of Kc. If I start by explaining it first, they don't ask for explanation again, they just want the effect. But I think it's easy if I start explaining it. The forward reaction is exothermic. The forward reaction release heat energy. Okay, that means when I increase temperature, what would the equilibrium do? The equilibrium will try to oppose the change. The equilibrium will try to decrease the temperature, but the equilibrium only knows, the system only knows to release heat energy. So to lower the temperature, to decrease the temperature, the reaction or the equilibrium will release less heat. How will the equilibrium release less heat? It will shift to the left to release less heat. That means to favor less of the forward reaction, it will favor backward reaction at higher temperature. When you favor backward reaction, you get lesser product, you get more reactants, and you also know that Kc can be affected by temperature. So because you favor backward reactions, so Kc value will decrease or decreases or get smaller, somewhere along those lines, as a result of the forward reaction being exothermic and your equilibrium favoring backward reaction, because your equilibrium will release less heat in order to counteract and oppose the increase in temperature by trying to decrease the temperature to shift backward, to favor backward reaction, to produce less product. Okay, so our graph, this is what happens. The equilibrium shift that way at higher temperature. What does our graph shows? Our graph shows y against A. So y against A. And what was y against A? You have the starting concentration of A mole per dm cube, and then you produce 2y mole per dm cube of Hi. Okay, so this is your product, this is your reactant. Okay, your product and your reactants. All right, not essentially exactly, but this represents the mole of the Hi, the concentration of the Hi produced, and we are producing lesser Hi. We are producing lesser Hi, and we'll have a bit more of the reactants. All right, so that means our gradient, which was a ratio of the product and the reactants. Okay, so that would tell us that the gradient is slightly steeper because, slightly less steeper, because we will have lesser of the product, okay, compared to the reactant, because the value of Kc will have decreased. Okay, you don't use a different colored ink, you just use one color, and it doesn't matter whether I've drawn this or this or this, as long as you have a less steeper gradient. So this has a less steeper gradient because the steepness of the slope is lesser, so the gradient is lesser, so you get lesser product compared to your reactants for a specific for that specific concentration of your reactant. You have lesser of the product as a result of Kc being smaller. All right, so your Kc decreases as temperature increases. All right, because your forward reaction is exothermic. So I should probably label it as, this is F part 1. So whatever, because everything will have been drawn in pencil. All right, so I would probably have to label it with F part 1 instead. Okay, F part 1. But I should be very clear, because this is the one with crosses, this is the one with no crosses. Speaking of crosses, this looks really anomalous. Maybe I just check back this point. This is 2.1 and 1.53, 2.1 and 1.55. Did it say 1.53? 2.1 and 1.53. 2.1 and 1.53. So that point is actually wrong as well, okay? So that should have been 2.1. Where's 2.1? 2.1. 2.1 and 1.55 is there. 1.5 is there. 1.53 is roughly there. Or maybe I was right. I don't know, okay? But I mean, that's still pretty close. Anyway, so we already established that the value will change as temperature changes based on Le Chatelier principle. I drew the line. I labeled the line. Draw and label the line at 1000 Kelvin. So I just labeled it F part 1. That should have been alright. So that's it on this paper 5 tutorial.